Thanks. I'll begin with a word of prayer. Dear Father, we thank you for the beautiful weather outside, for the weekend. Just pray that you help us today to just learn a little bit more math together, to focus, to just draw our ideas together. As the students work on completing this semester, I help them to finish well this semester for your glory, Lord. In your name I pray. Amen. All right, let's see here. I have a few more tidbits. I'll try to leave some time for homework questions at the end of today. And so, if we, so a couple things on and I was glancing through your book, I didn't see it. It might be in there somewhere, I just didn't see it. But if we, so I want to talk a little bit about the combination of polar coordinates and parametric viewpoint. I mean, in particular, let's see here. So, just a couple of points, just kind of big picture points here. If we have, and this, I'm not even talking about. I'm going to start by not even talking about the polar viewpoint. I'm going to start talking about the Cartesian viewpoint. Take us back to where we started before all this stuff, right? You looked at graphs like y equals f of x, right? Say a less than or equal to x less than or equal to b. If you're looking at the graph and you want to describe its arc length, what would you do? You study, basically you set x equals to t, right? So you've got this parameterization r of t, something like t comma f of t, right? Which gives us a velocity of what? The velocity at time t would be like 1 and in df dt, right? This is the velocity. And then the magnitude of the velocity is what we call the speed, right? So what's the speed? We take the square root of the sums of the squares of the components, right? So here this is 1 squared plus df dt squared. And that gives you the speed, right? So the arc length, S, all right, total from A to B, let's see, that's total, let's call it for a second, is equal to the integral from what? From A to B of the square root of 1 plus df dt, quantity squared dt. Now, in this context, your textbook and other textbooks would tend to write this as just S total equals what? Integral from A to B, square root of 1 plus, say, dy dx squared dx. And that makes sense because x is equal to t here, so we can parameterize everything in terms of the x variable just the same. I just changed x to t to try to emphasize the viewpoint here. Right. Did I talk to you guys about the arc length function at all yet? What's the difference between total arc length and arc length function? So let me just kind of walk you through it here for a second. So suppose we're looking at this curve, right? And it starts at x equals to a in this case, right? The arc length function would be something like, say we go over here to x equals to t, right? I want to know what's the length of just this much. How would you obtain the arc length function? It's not. What would the formula be for this so-called s of t? You do what? Integral from a to what? To a to t of the speed, right? Sorry, I'm going to shy away from the prime notation here. I'll use df dx, it's easier to see. Well, let me use y, dy dx. So there you go, that would be the arc length function. Does that make sense? What should that be consistent with? What else did I tell you guys the other day? ds dt, right? Remember I derived it somewhat heuristically over here. I explained to you why the ds dt should also be equal to the speed, right? So now I'm telling you s as a function of time is equal to this integral. If that's going to be consistent with my other claim, which I made through geometric heuristics, that the speed is equal to ds dt, how can if these are going to be consistent, what can you check now? You can check what? Is it true that d dt of s of t is really equal to the speed, right? d dt of what then? In this specific example. I mean, I'm doing this check for a specific example, but the derivation I'm doing right now, guys, is more general. You can define arc length as a function of time more generally than this. I'm just exhibiting this idea for this example. What is the derivative of an integral with a varying bound? Remember, fundamental theorem of calculus part 1 says you just do what? Take this, right? And plug in what? X equals to t in this case, right? So this would be square root of 1 plus basically dy dt squared. In other words, it's the speed at time t. So if you don't like the way I quote-unquote derived the speed over here the other day, you could define arc length as a function of time by just integrating this quantity, the magnitude of the velocity, over the requisite parameter domain, and from some base time to the time you're interested in, or in this case x you're interested in, and that will give you the arc length as a function of time. And by the fundamental theorem of calculus part 1, it will be the case that the arc length as a function of time, that ds dt is in fact equal to the speed. I didn't use any geometric hogwash to derive that ds dt is equal to the speed this time. It just was calculus, you know. All right. So I'm getting a little bit off track here, but these are some of the things I told the other sections, so I probably should tell you guys as well, to be fair. Now 2, so this is all just, really the point here is the formula for the Cartesian coordinates is just that, right? Now what's it look like in polar coordinates? How do you, all right, fine, let me get out of my system here. General comment. I'm sorry, I seem to have worked myself into something here. You can define s of t by the integral, say, from some t naught to t of the square root of dr dt dot dr dt. I shouldn't use t because I'm using t up here, so we should do something like dr du, dr du, du, something like that. This defines arc length of r of t with base time t naught, right? So in other words, here's a picture of what's going on. You've got some parametric curve, right? I don't know what it looks like, whatever it's got. Hopefully it doesn't have one of those. One thing about a smooth curve, right? There's some particular point that you're starting at, r of t naught, or it could be in the middle, whatever. And then the point is s of t will give you the arc length of the curve up to r of t. So this arc length is s of t. It's a function of t. As t goes on, the arc length increases, right? And you can prove, fun fact, we just derived it for the specific example, but it's generally true, that ds dt is equal to the length of dr dt, aka the speed. All right. That's all I have to say about that. Unless, of course, there's a question. But now, I've mentioned to you guys you can look at different parameterizations for a given curve, right? A given curve doesn't have just one parameterization. You can use different ones. And so one of the things you could do would be you could calculate the arc length for a curve, right? And you could use that to parameterize the curve instead of a given parameter, right? Would you guys like to see an example of that before I get back to my polar thing? Yep.
What are the double bars around?
Oh, that means length, like the length of a vector.
Okay.
So for example, the length of the vector 1, 2 is the square root of 1 squared plus 2 squared, for example. Yeah. I may have written that once before, so it's fine. It's understandable. You guys have not absorbed that. I'm kind of nervous about introducing this concept without giving you at least one example. Let me give you one example before I get back to my stated goal, which was to describe parametric stuff. So what about a circle? That one's pretty easy. Right? Circle, let's see, that would be what? X equals to r cosine t, y equals to r sine t, something like that, right? So if we look at it as a vector, the path is r cosine t, r sine t. What's the velocity? Yeah, negative minus r sine t, and then what? R cosine t. Okay, so what's the speed? Looks like the square root of minus r sine t quantity squared, right? Plus the quantity r cosine t squared, which is just what? By the way, what do we assume about r? We assume r is positive, as to avoid annoying cases to talk about. So what happens here? You get what? R squared sine squared t plus r squared cosine squared t, which is just what? Sine squared plus cosine squared is 1, right? So this simplifies to the square root of r squared. R squared being positive, this is just r. So the speed is r. So if we calculate the arc length as a function of time, say based at time 0 to time t, we would have to do something like integrate r du. Because the speed at time u, right? This is, by the way, this whole thing that I just wrote over here is nothing more than the length of the velocity at time u, okay? That is the square root of dx du squared plus dy du squared. Anyway, so for the circle, bless you, what do we got? Basically, I'm saying, what is the length of this arc? r times t, right? It's pretty simple, right? So what happens if we put t equals to 2 pi? I think we already did this one, right? Did we already do this? I can't remember. A little bit rusty from last week. I need to go watch the video personally. That's the real reason I tape, so I can remember what I actually did. Oh no. That hurts me somehow. Look, as t goes to 2 pi, we get the what? Circumference of a circle, right? But there's something else you can do here which is a little bit weirder in terms of how can you reparameterize a circle? What are other ways you could parameterize a circle? You could do something like this, R2. You could use S as your parameter instead of t, right? And so basically we found that RT is equal to S. So if I solve this for t, what do I have? I've got t is equal to S over R, right? So if I plug in S over R everywhere I had t in my original parameterization, this will give me a new parameterization of the curve, like this. R cosine of S over R, R sine of S over R. And what's the domain of S now? To be clear, up here I should have told you what the t 0 less than or equal to t less than or equal to 2 pi, right? For example, what would the parameter domain be for the arc length parameter? I have to multiply that by r, right? RT is equal to S, so I have 0 less than or equal to S less than or equal to 2 pi r. So this gives us a new parameterization of the circle. Why would you care about this? One of the reasons you might care, right, is we have all these different choices, excuse me, choices for parameterizing the circle. It might be nice to have one that's sort of unique, right? So once you pick a base point, there's only one arc length. I feel the same way. There's only one arc length, one arc length parameterization of the circle going forward. Like this, there's lots of different choices of parameterization, right? Once I pick this as my base point, like this starting point here, and I say I'm looking at the circle going, that way, counterclockwise, this is the only arc length parameterization of the circle. This is a unique choice. So that's one nice thing, right? Because it's kind of annoying to have infinitely many parameterizations. Here's a unique one. And this is also tied to the geometry of the curve, right? Like the arc length is something geometric, it's something intrinsic. We could have talked about arc length without ever whispering a word about parameterizations, right? What would be the speed for R2? What happens if you calculate dr d2? ds, what's that equal to? Chain rule pulls out a 1 over r, right? So I get minus sine of S over r, minus, well, not minus, but just cosine of S over r, right? S is the variable. ds, I'm calculating the derivative with respect to S. What's the length of that vector? It's the square root of sine squared plus cosine squared, right? Which is 1. Does that make sense? Right? I think it does. Let me show you why. So this is also supposed to be what? ds dt, right? But what is t in this case? T is equal to S, right? So I'm just showing you ds is 1, right? Which is good. Should be, right? So this is sometimes called the so-called unit speed parameterization of the curve. So as you take Calculus 3, I hope you'll study this further. For three-dimensional curves, the unit speed parameterization of the curve is useful to understand the geometry of the curve. Anyway, I'll just say that much and stop there. So finally getting to 2, unless there's a question, I'll start into my second point, was polar equations. And I don't know if this is in the book as it ought to be. What if you have a curve described by r is equal to, say, g of theta? So in other words, you have a curve which is described in terms of polar coordinates. How would you calculate the arc length of such a curve? What's a good way to do it? Well, I would recommend that we use what? The path nicely given by what parameter? We choose t equal to what? Well, it's equal to theta, right? Theta is a good choice of parameter in this case. So if you do that, then what do we have? We've got x equals to r cosine theta, right? And y is equal to r sine theta, but what does that actually look like here in terms of time t and the function g? That's just what? That's, well, what is that? That's g of t. And then cosine t. And this is g of t. And sine of t. Again, t is equal to theta, but I'm just trying to use t across all my examples so that you understand the role of the parameter. And so my path, all right, written as a vector, would be this. Or if you like, if you'll allow me, I'm just going to write this g cosine t, g sine t, because the t dependence on g gets kind of old after a while, all right? So what's the speed then? So this is x, right? This is y. And the speed should be what? The magnitude of dr dt, right? But that's equal to what? Square root of dx dt squared plus dy dt squared. All right, so what we want to do then is calculate dx dt and dy dt. We're actually going to find that there's a really beautiful, simple formula for calculating the arc length of a polar curve. I want to derive that for you guys so you can use it. And I hope you understand the derivation we're going through. It's not that complicated, but it is nevertheless one of the longer calculations we'll do at the moment. So here we go. We got x equals to g cosine t, y equals to g. I'm just writing them again to have them close to where I'm working. So what happens if we calculate dx dt? What happens if we calculate dy dt? I'm going to write down the derivatives, and then I'm going to write down their squares over here. So this is going to be a somewhat wide calculation, all right? So dx dt is, well, it's g prime cosine of t minus g sine t. And dy dt, well, that's g prime sine t plus g cosine t. So we can calculate dx dt quantity squared, and we can calculate dy dt quantity squared. Why did I have two terms? What am I doing here, guys? What is that? G is a function of time, right? Product rule, right? And I have to do the product rule. Now I got a square, right? So square, you just FOIL it out, basically. What do we got? We got, like, we've got g prime. I'm tired of the g prime. We've got dg dt. It's easier to see. Squared. Cosine squared t minus 2g dg dt sine t cosine t, and then plus g squared sine squared t. Down here I've got dg dt squared sine squared t let's see here, plus 2g dg dt cosine t sine t plus g squared cosine squared t. I hope you're not mystified by what I'm doing. All I did was just to square the derivative of x and square the derivative of y and just write it out. I'm doing this because my goal is to calculate the speed, which is the sum of dx dt squared plus dy dt squared, right? So you take this and you add it, and we've got ourselves dx dt squared, right, plus dy dt squared is equal to what? Well, see what happens here? Sine squared plus cosine squared gives us what? 1. So we have dg dt, it's a quantity squared. These guys cancel. Wonderful. Because those are ugly. But these are pretty. See this? Sine squared, cosine squared again. Common coefficient of g squared. So we just get plus g squared. Or if you want me to, so there it is. I mean, therefore, the arc length, S, would be what? It would be the integral, say, from theta 1 to theta 2 of the square root of g of theta quantity squared plus dg d theta quantity squared d theta. I put theta back. I put t back equal to theta now, right? Of course, I personally like to look at this in terms of the r instead. So like you could also write this with the understanding that r is a function of theta, right? With the understanding that r is a function of theta, we could also write this like r squared plus dr d theta quantity squared d theta. Any questions? So, you know, for a graph, right? For a graph, we have this kind of, like, you could say, kind of black box special formula, right? If you just have y is equal to a function of x, then we can use this to calculate the arc length, right? If we have the curve described parametrically in terms of polar coordinates, we can use this formula over here to calculate the arc length, right? But both of these are just special cases, right, of the more generic formula, which is what? Both special cases of what? Our general arc length formula, which is what? Integral from a to b, let's say, or let's say t0 to t1 to t2, maybe that's better. t1 to t2 of the square root of dx dt squared plus dy dt squared. And I have tried to emphasize to you guys that this formula is really a natural outgrowth of looking at the speed of the velocity, right? To look at the magnitude of the velocity, integrate ds dt with respect to t, that gives you the net change in arc length. I should show you guys, there's another heuristic viewpoint which is useful here, right? So there's this so-called infinitesimal, so you can look at it this way. And sometimes I've done this, and this is the way I've taught it in the past to engineers, and they found it, they liked it. So you guys can see what you think of it. Basically, this is the infinitesimal thing. You have ds squared is equal to dx squared plus dy squared. What I'm saying is an infinitesimal change in arc length squared is equal to a little bit of x squared plus a little bit of y squared. And then you can just play games with this, basically. Like, number 1, divide by dx squared, right? What does this give you? It gives you ds dx quantity squared is equal to 1. Well, let me write it out. Dx squared over dx squared plus dy squared over dx squared, right? Which is equal to 1 plus dy over dx quantity squared, right? So therefore, ds dx is the square root of 1 plus dy dx squared. And then you just multiply dx to the other side, and there you have it. There's the formula for the arc length of a graph. Then you can, the other way to go about the second thing I did today so far would be to do something like draw yourself a little tiny triangle, like so. So on the one hand, you have this like ds here, right? The curved arc length. And this is r, and this is, okay, that's r plus dr, but it's essentially the same thing. All right? And this is a tiny triangle. So d theta, basically ds, so we have ds is equal to what? It's equal to r d theta by the definition of radian measure. And on the other hand, we have what? On the other hand, we could look at ds in terms of a little triangle. All right? The little triangle I would look at, not the big triangle. Well, they're both triangles are tiny. Okay? But let's see here how to say this. You could also look at it like, you know, so here's my little dy, here's my little dx down here, right? Something like that. So you'd have ds squared. Oh. Okay, so ds squared, that's not quite the thing I wanted to write. On the one hand, you could say, I have found a way to make this confusing. I'm sorry. Let me try this again. I seem to have lost my way. All right. So I only really care about the tiny triangle. See if I can do it. Oh man, I have. Oh no, oh no. It has left my mind. There's a triangle I can draw to convince you that ds squared should be also equal to dr squared plus r squared d theta squared. I guess it's just what I was drawing. I can't think of a better way to draw it at the moment. It's bothering me. Sorry, guys. So this, man. I'm sorry, I can't think of how to draw this picture. Oh. Well, what am I looking in? The book's not going to have this picture. What am I looking for? I mean, in some sense, it doesn't matter, right? I showed you an actual, somewhat rigorous way to derive it over there. Sorry, I'm missing some words here. There is some picture that can be drawn to support this, and so I mean, of course, this is the infinitesimal length that corresponds to looking at r shifting a little bit, right? If you look at a little polar sector, something like this, right? So this distance would be like dr. We're going from r to r plus dr, let's say. And suppose we're going from, say this is theta, and then over here, this is theta plus d theta, right? So this would be dr. And if you wanted to be somewhat picky, although I don't know how picky you're being when you're doing infinitesimal arguments, but this right here is r, that's d theta. That would be that arc length. And then out here, this would be what? This would be r plus dr times d theta, right? And so, anyway, my point is that r d theta is like the arc length subtended as you go along an angle being changed with the radius being fixed. And so if you think about like a little infinitesimal length squared, and you want to do it in terms of polar coordinates, you have the distance in the radial direction squared plus r d theta squared. This gives you the net distance in terms of polar coordinates. And then if you take this thing, right, and you divide by d theta, what do you get? Or here, let me be even more direct. You can rewrite this as what? This is dr d theta quantity squared plus r squared. Pull out the d theta squared, right? So ds is the square root of r squared plus dr d theta squared. So once you understand that heuristic principle I'm talking about, it's easy to see where that integral formula comes from. So once you can express the infinitesimal arc length squared, the ds squared, in terms of your coordinate system, then you can calculate the arc length shortly thereafter, especially if you look at curves which are parametrized by one of your coordinates. All right, I'm getting off track. So let's work an example. Do you guys have any? Oh, I think I said I'd take your homework questions. I guess now is a good time as any to do that. So let me open up the floor. We're now, basically, guys, by the way, we're essentially to where the section 2 got to this point last Friday. So now we're a full day behind the other section somehow. Sorry about that. But it's not the end of the world. So if you want to watch what's past this point today, if you don't want to wait, then if you watch section 2, then that'll be like tomorrow at the moment. Something like that, just to let you know. I know some of you have exciting tests and things later this week, right? So if you wanted to get ahead in here, a simple thing you could do would be just to watch lecture 2 from today, then you wouldn't need to come tomorrow. Wait a minute, no, that's not quite accurate, but you'd be able to get ahead in your homework anyway, at least, something like that. Oh, I don't know, do what you want. Let's see here. Does any questions? Seven 7.2? Oh, okay. It's like, what? That does not compute. 26. You said 26 and 7.2. 10.2. I'm sorry. Apparently, I want to go back to. I missed chapter 7. Apparently. So you got positive radius 1, positive radius 2. The difference between your angles is less than pi, right? The distance formula you found in 25 reduces to the law of cosine. So I guess you could start with the answer from 25, right?
Yeah, I have that.
Yeah. Okay. Yeah. Oh, by the way, before I forget, a nice example to follow up on this one is if you just look at r equals to theta, you get the arc length for that curve is the integral from theta 1 to theta 2 of the square root of 1 plus theta squared d theta. And that'd be a pain to actually work out, but there's a nice example where you could actually do, and that's that, remember that spiral? So like with this way of thinking, we could actually calculate the arc length of a spiral if you wanted to. Sorry, my brain is skipping a little bit this morning. I think you may have noticed. Actually, what I'm planning to do today in the later section, guys, is to derive the arclength formula from a Riemann integral argument. And since we're a little bit behind in here, I think I'm going to skip that with you guys. If you want to watch that, you can. But I'm just going to go on with the like calculation of surface area and more area examples and that stuff tomorrow. And hopefully well, actually, I think the thing that we're still missing conceptually is the how to find the tangents to parametric curves. That's the one major kind of conceptually different topic we still have left in this chapter. Okay, so where were we? 26. Can you tell me what the formula is, or?
D equals the square root of...
D equals the what?
Square root.
Uh-huh.
R1 squared plus R2 squared minus R1, R2.
2R1?
R2.
You mean 2 times R...
Multiply.
2, you mean 2 times R1 times R2?
The cosine of theta 1 minus theta.
So the point is you got 2 points in the plane, right? Point 1 and point 2, whatever. Maybe I should make this point 1. Make that point 2. And this is the distance between them, right? I guess my question to you is, what's the law of cosines? Forget about R1 and R2 and theta 1 and theta 2. What's the law of cosines? If I draw, let me just give you a slightly more leading question. Suppose I have this triangle here like this, right? This is A, this is B, this is C. That's theta. What's the law of cosines?
A squared plus B squared minus 2AB cosine.
Yeah, equals what? C squared. Yes, we have a winner. Very good. So the goal is to somehow derive that from this, right? So I suppose what I would tend to do, I might look at this triangle maybe, because then this theta, this would be my quote-unquote theta, right? What's assumed in here is that what? Right, theta is 0 is less than theta is less than 180 degrees, right? So that's what you're given, that the theta 1 minus theta 2, right? You're given the absolute value of theta 1 minus theta 2 is less than pi, right? Or 180. Which is to say that this, and that would be theta here, right? If this is theta 2, right? And this is theta 1, then theta would be theta 2 minus theta 1. However you order the points, it doesn't really matter, right? Anyway, the difference in the thetas would be the interior angle to that triangle, right? Oh, and what else? Oh man, I think if I write much more, I've solved your problem. This is R2, this length, right? And this is R1, so I would just start making a dictionary, right? Like R1 is A, R2 is B, and C is equal to what? D. I think we're done. Sorry. There's not much to do here, really. It's mostly a question of interpretation. So, I should have asked you guys to do number 25. That would have probably been more interesting, right? Oh, okay, cool. It's been a few months since I picked out these problems, you know. Let's see here. Other questions? Oh man, I tell you what. I did not give you permission to restart and put updates in, you worthless piece of garbage. Oh, that makes me angry. Windows restarted itself. I didn't tell it to. Oh, I tell you what. I've tried my best to not let it restart and install its insidious automatic updates. But no, I don't know best. It won't let me have my way with my own computer. That's not what Microsoft wants. I'll tell you what. I think I'm going to Linux next computer. I've had it. If I want to turn off the automatic updates on my computer, let me turn off the automatic updates on my own computer, Microsoft. Worthless. Sorry, I get upset. No internet connection. Updates were installed. You don't say. You don't say. You guys have other questions? Not at the moment?
56 from 10.2.
56 from 10.2, you say? I have your test graded, so I'm trying to put the grades in here. You want to give them tomorrow? What's that? Oh. Stop recording. Yeah, go ahead and stop recording.